Okay, what I'd like to do is just go through two questions in my book on page 97, the Engineering Studies Workbook, which is the red one. I'll start by going through question 2 and try to make it as simple as possible, this concept of method of sections for finding out individual member strengths in a truss. So if you have a look at this question here, I'll just put the annotator on. So what you're asked to do is to determine the forces in member A, B, and AB and BC, and the reactive force at support A. Now, when they say a reactive force, that means that you can't just give the components. You've got to work out what the single force is, and it's just a matter of Pythagoras, but I'll go through that with you. So the first thing that we want to do is find these reactive forces, because we're going to use those to find the force in AB. So you're not asked to find the force at E, so you don't find that force. And I want you to always do this with a roller reaction. I want you to make sure that you tell the examiner that that is at 90 degrees to the roller, to the roller surface. This sense here, you're not sure of, so you can put a question mark there if you want, but you can see that if you're applying this force and that force to this, the reactive force must go to the right there. So always put that in, because that will gain you marks. So let's see how we do this. So we're going to take moments about this point here to find the horizontal component of that force there. Now see this vertical component of the reaction at A, that this should go through A there, because there's no perpendicular distance there, that's not given. So this should be at A there. So some of the moments about E, make sure that you put this statement equals 0 with clockwise positive. So we've got RAX, that's the horizontal component of the force at A, multiplied by the perpendicular distance, which is 0.7, and that's going to go anti-clockwise. Now, we're not sure of that either. So if we get a negative answer here, it's telling us that it goes clockwise. So we've got RAX times 0.7. We've got 0.5 times 1, which is clockwise, 2 times 2, which is clockwise, which equals 0. So therefore, we've found that the horizontal component at A is 6.43 kilonewtons, and it's going to the left because we got a positive answer there. And to find the vertical component at A, the vertical component, because this force here cannot resist a vertical force, the vertical component is that force, which has got to equal that force plus that force. And this is how you state it. The sum of the vertical forces equals 0 with up positive. So we've got RAY, which is going up, which is positive, minus 0.5 minus 2 equals 0. So we've got a positive answer there, so that definitely goes up. And so that's 2.5 kilonewtons going up. Now, because the reactive force is asked for, it's not the reactive components at A, you've got to use Pythagoras here to find the magnitude of that force, and you've got to find that angle as well, because remember there are 4 components of a vector that you've got to include in the answer. It's magnitude, sense, direction, and point of application, but you already know that the point of application is A. Okay, so that's how you get the force at support A. You can't use the 3/4 rule because there are 1, 2, 3 forces acting there. So this is the way to do it, taking moments about E. Forces in A, B, and B, C. Now let's have a look at the force in A, B. Now I've taken a section through here, you know the theory behind this, but I'll go through it again. If you cut a truss and you want the other half to remain in equilibrium, the forces that were in those members before it was cut has to equal the forces that have to be applied to those members to keep that section in equilibrium. So, let's say that we've taken a section through here, and we're going to take the, what section did I take? The left-hand section. Okay, so these cut members here, I've put them in tension, and I'll put a question mark there. Now, I haven't actually shown these in tension here because I'm going to take moments about E. Now, the reason why I'm taking moments about E is to eliminate the moment of that force and that force. So the idea is that when you cut this, this section of the truss has been removed. So these cut members, they were once internal reactive members. Now, I'll just go through that with you now. So let's just say that this member here is in compression. And so that will, let's just say this member here is in compression. So that force will go towards the joint, and this force will go towards the other joint. And the way that I want you to remember this is that you look at these two forces here. They're pulling apart, and you think, oh, it's tension, but they're called internal reactive forces. And I don't want you to worry about that in an exam. This is the way that I want you to figure out whether that shows compression or tension. You get your hand, you put your hand, your fist at that point there, and put a pencil in your hand and do what that force is telling you. If you push the pencil into your hand, you can see that it's in compression. Same thing here. Put your hand there with a pencil in it and push towards the joint, and it shows that that member is in compression. So don't get foiled by the fact that this looks like tension that's pulling it apart. They're internal reactive forces. So just use that method of determining whether they're in tension or compression. So I'll this is what I always do. I put them in tension with a question mark there because I'm not quite sure whether they're in tension or compression. Now, we don't want that force. We don't want that force. And remember, all this is gone. There's nothing there. You're just left with these broken members there, these cut members. And all this here has to be in equilibrium so that the cut section remains stationary in equilibrium. Now, if you were to take moments about this point out here, if you were to take moments about that point there, about regarding this cut truss that's shown here, some of the moments about that point have to equal 0 because this cut section is still in equilibrium. But you don't take moments about a point there. You can take moments about B, C, anywhere, and the moments, the sum of the moments will equal 0 for this cut section. But it's silly to take moments about a point where it's not going to eliminate the two unknown forces here. So you look around and see where these two forces meet, because that force there is the one that we want to find. And so you look around and see where these two forces meet. So you take moments about that point there, because the moment of that force about that point 0, the moment of that force about that point 0, and that force goes straight through that point. So the moment of that force about that point is 0. So all we've got to worry about is that force there, right? And so we take moments. So it's 6.43, we've worked out that it is 6.43, there it is there, right? So that force multiplied by that distance equals that force multiplied by that distance. Now, you don't have to do all this. All you need to do is look at that joint there, and if there's no other horizontal force acting here at that joint, that force has to equal that force to balance it. So you don't really have to do that. You'll know that the force has to oppose the applied force. So that force there is equal to 6.43. Now, I just did that to show you how it works out to be the same, because it's hard to see that if you don't see the calculations. Okay, the next thing that I want to do is I'll get rid of all of this. Is we've got to find the force in BC. We've got to find the force in BC. Now, you know the theory behind this now. You can cut 1 member, 2 members, 3 members, but no more than 3 members. So I'm just going to put my section in here. Make sure you use a chain line for the section, because it shows the examiner you've been taught correctly. And so this part of the truss here is the one that is left out in space. And you've got to apply forces. I'll just get rid of these here because we're not sure about those. So what we've got now is this section is gone, and all we're left with is this part of the truss. And I'm going to put in the that as a tensile force there, and I'll put a question mark there, and I'll put that as a tensile force there. I'll put a question mark there. And so the idea is to find, we don't want that force there. The idea is to find the point that will eliminate that force if you take moments about that point. And the obvious one is D there. So if you take moments about D, and you've got to find that perpendicular distance, because a moment is force times perpendicular distance, you can take moments about D and you'll be able to find the force at BC. And I'll show that you can use the method of joints with this too. I'll show you that in a moment. So you find out what the angle is, what theta is there, which is 35 degrees, and then you can easily find out what D is there. So some of the moments about D equals 0. So we've got minus BC times 0.573, which is that distance there. And we've got this force here. We don't worry about that force. We don't worry about anything over here. But remember, you can still take moments about, even though this isn't there, you can still take moments about anywhere to find the forces. But the idea is to take moments about a point that will eliminate the unknown forces. And in this case, it's D here. So we've got minus BC times 0.573, which is that going anti-clockwise. You've got 2 times 1, which is going clockwise, which equals 0. And so BC is equal to 3.5 kilonewtons. And because it's positive, that is correct. It's in tension. Okay, that's that method. Now I'll just go over to the next question. Okay, can everyone see that question?
Yeah.
Okay. Now this is a difficult one. This was asked in an HSC quite a few years ago, and it caused a lot of grief. So, well, for the truss shown below, determine the components of the reaction RL. Now remember I told you at one previous lesson that generally the parts of the question are designed to help you with subsequent parts of the question. So the components of the reaction at RL. So we've got to find the horizontal component and the vertical component at RL. And you don't have to use Pythagoras to find out the actual reaction at RL. The question has just asked you for the components, and that will probably help us later on. So and then we've got to find the magnitude and nature, either tension or compression. That's what nature means, tension or compression, of the force in member AB. Now, there's AB there. This gave the students a few hassles because they had to use trigonometry, and it's a bit of a roundabout way. But I'll show you a quick way of determining D if the trigonometry mucks you around in the exam. So let's find the vertical component, which will be RLY. And I'm saying that vertical component is going down because you have a look at this truss. If you've got a clockwise moment produced by that force and a clockwise moment produced by that force, you take moments about that point there, you've got to have an anti-clockwise moment produced by that reaction. So that's why I've put it going down. It just saves you nutting out. You know, if you get a negative, it goes in the other direction. So I've put that force there. Make sure you put it in to show the examiner where those forces go, and make sure you name them because it makes life easy for the markers and for you when you're working it out. So we're taking moments about RR with clockwise positive. So we've got RLY times 3. So we've got that multiplied by that perpendicular distance, and it's going anti-clockwise, so it's negative. Plus, we've got 30 times 9. So you've got 30 times 3, 6, 9. And that's going clockwise. And don't forget this one, because if you've got a perpendicular distance between the point of moment that you're taking moments about, it's going to create a moment. So that's 10 times 3, given the perpendicular distance there, equals 0. We've got a positive answer, so we've got 100 kilonewtons acting down. To find this force here, that has to equal any other horizontal force there. So obviously that's got to equal that 10, and it's got to go in the opposite sense to that. And this is how you set it out. Some of the forces at x equals 0. X is the horizontal component, so we've got RLX minus, which is going negative. I've put it negative because I could see that's positive, plus 10. So we've got RLX equals 10. Positive answer, so therefore that's correct. Now, what we've got to do is we've got to find the force in AB here. This is part 2, or part B. So I've put a section line down there, and I'm going to have these forces broken, I'll just draw them in. So this force here, I'm going to say that's tension, question mark. You don't have to put a question mark, you just realize that you don't know what sense it is. And that's a question mark there. And I'm saying that AB is tension as well. Now, I'm going to take moments about a point that has to eliminate that force, because remember, this is cut here, all this part of the truss is eliminated, and I've put down here using this section, assuming AB is in tension, right? AB is in tension, and considering the right, the left-hand side. We're considering the left-hand side. I'll put the right-hand side there for some reason. Okay, so let's, we've got to find this perpendicular distance. Now, we're going to take moments about a point that will eliminate those two forces. And so the first thing you do is to move your eye along and find where they meet. So we're going to take moments about Z there. And we've got to find this perpendicular distance here. So the idea is the first thing that you do is find out that angle. I'll go through the trig and then I'll go through this scaling method. So you find distance x there, where you've worked out what theta is. Theta is 12.09 degrees there. And we can find out what the angle alpha is up there, and then you can work out what the distance is, because we know what the length of the hypotenuse is there, and we know what that angle is now. And so once you've found out what Z is, you can work out what that distance is there, and then you know what that distance is there, and then you can find alpha. And so you can work out what that distance is there, D, you know the angle, you know the hypotenuse of that triangle, so you can work out what D is, which I've done here, which is 8.65 meters. Let's do it by scaling. Remember, all of your drawings in the HSC will be scaled unless they say it isn't. Now, that happened a year or two ago, and people opposed that, so I don't think that will happen again. I think every drawing that you'll have in your HSC will be scaled. So this is how you do it. So 17, by scaling on the diagram, 17 millimeters, 3, 6, I don't know where I measured that 17 from, but anyway, 17 meters on the diagram, it works out to be 85 millimeters. Like you can say 5, 8, 11, 14, oh, there it is there, that's 17, right? So that distance there on the diagram is 85 millimeters. So therefore, if you scale off D, you measure, you've drawn this accurately at right angles, and you measure that distance there, and it works out to be 43 millimeters. So,
excuse me, Mr. Rochford.
Yeah.
Your screen's gone off for me just now.
Oh, has it?
Not sure about the others, but for me it has.
What about the others?
No, I can see it.
Hang on. I might just try rejoining the Zoom and see if that fixes it.
Okay. Okay. I'll have a look and see when you come on. Okay, so let's just keep going. So just to I'll just admit Will. Okay, you're right, Will.
There we go. That's fixed it for me.
Okay, good on you. Thanks.
Okay, thank you.
Okay, I'll just go through this again by scaling. Look, that's fairly difficult, all of that, using trig, particularly when you're stressed in an exam. And this is a good technique. So what you do, I'll just go over what I just said. That distance from there to there is 17 millimeters. So you say 17 millimeters equals 85 millimeters. You've measured it. And then you construct this accurately, and then you measure that distance there. And that's 43 millimeters. Now the ratio, 1 millimeter is equal to 17 over 85. So you multiply it by 43, and that's millimeters, millimeters cancel, and you're left with meters. And so you've got 8.6 meters. And see how accurate it is. It's a very accurate way of doing it. Okay, so let's, using the section, assuming AB's in tension and considering the right-hand side. Now, so I've got AB times 8.65, so we've got that going anti-clockwise. We're taking moments about Z because we want to eliminate that force and that force. Don't forget you can take moments about anywhere, but if you don't want to end up with 2 or 3 unknowns in the equation, if you took moments about that point there, for example, you'd have 3 unknowns in the equation. You'd have that perpendicular distance, and that perpendicular distance. So the idea is to take moments about a point that will eliminate the 2 of the unknowns that you're not asked to find. So we're taking moments about Z there. So I've got AB times 8.65, and I've said it's going anti-clockwise. We're taking the right-hand side here. Minus 30 times 5, 30, there's the 5 there. That's going anti-clockwise, so that's negative. And you don't worry about that force there because you're taking moments about that point. And so that equals 0. So therefore, AB is equal to 7.34 kilonewtons in tension because we got a positive answer there. And I've said that that member is in tension. Is that okay?
Yeah, that's pretty good, thanks.
Yep.
Okay, any, do you want me to go over anything at all? Or are you pretty right? If I were you, I'd give those
I'm
2
pretty
questions a go on page 97. And
Yeah.
I'll see you soon, and I'll be going over this thoroughly, and I'll be sorting out any problems that you've got. Okay, I'll let you go.
Thank you very much.
Okay,
Thank you.
well, I hope that sorted it out for you. So,
Yeah.
okay, thanks, fellas. I'll see you soon.
Thanks
Yeah.
heaps.
Okay, bye.
Bye.